All right, coming back from the practice problem you just tried where I wanted you to find the standard deviation, you should have gotten 3.46. You could have rounded it, you might have rounded it to 3.5. We had a discussion in class today about the rounding. On the test, I'll try to say what specifically to round to. Other than that, if you show your work, I'll be able to see that you got the right answer. If you rounded differently than I did as far as you rounded to more numbers or less numbers, or maybe you rounded along the way, which I don't recommend. But I'll be able, it won't be that big of a difference. I'll be able to tell how you got your answer. If you wrote 3.5, I would have known that you just rounded to the 10th place instead of the 100th place. I didn't really specify in the problem, so don't stress too much about it. All right, so going through, this is what we should have gotten. I found the mean of all the numbers. I then found all the deviations. So I found about how far all of these, all the actual data values were from that mean, right? Then I squared them. Once I squared them, I added them all up, got 60. Divided 60 by n minus 1, meaning the number of data items minus 1. I had 6 data items, subtract 1, it's 5. So 60 divided by 5 is 12, and then finally took the square root of that. So my standard deviation is 3.46. Okay, so my average is 5. I look at all this data. The average is 5. Average number, they hover around 5, give or take 3.46. So the one standard deviation away would be 3.46. So most of our data is going to fall within, in like around 3.5 above or below. That's kind of what that standard deviation is saying. It's saying most of the data is within kind of 3.5 units from the mean. All right. Moving on to z-score. So z-score is a measure of position. All right, it measures the position of an item within a set of data. So each individual item in the sample can be assigned a z-score, which is the first measure of position, all right, that we kind of look at. So up till now, we've really been finding the formulas we've been using to find these different measures of data, like like the mean, the standard deviation, the mode, the median, all that. Those were one number representing an entire set of data. Okay, so that was for an entire set of data. Z-scores are for the individual pieces of data themselves. So for instance, in this problem, right, this is this is the mean of the whole set of data. This is the standard deviation of the whole set of data. Each one of these individual pieces of data would have a z-score. Okay, so and the z-score measures its position within the set of data. So the smallest number, right, would have the smallest z-score, so on and so forth. Okay, and the z-score kind of measures how far away you are from the mean, right? So let's look at that real quick. All right, so here's an example. If X is a data item, so this is the formula for how to find a z-score. You're going to do the data item itself minus the mean of the whole set of data divided by the standard deviation. So if you're going to find a z-score of an item, you're going to need to know the mean and the standard deviation of the set of data that item belongs to. So looking here at this, what we just did, so that set of data that on the previous page, right? We found that the mean was 5, the standard deviation was 3.9. I just noticed a mistake here. Oh, typo. 3.46 it was supposed to be. All right, well, let's not worry about it. Let's pretend it was 3.9. Oh, gosh. All right, so let's pretend it was 3.9. If I wanted to find the z-score of each of these pieces of data, I would just use that formula. I would do, so the z-score for 5, right? I would do 5 minus 5, right? Minus the average, and then divide by the z-score, and the standard deviation, and that is 0. Which makes sense because if your standard deviation is kind of showing if your z-score is showing, your position in regards to the mean, right? How far away you are from that mean, if the mean is 5. So if you have a score of 5, 0, you are positioned right on that mean, right? Here, 8 minus 5 divided by the standard deviation, 0.769. See how this z-score is a little higher because it's higher, it's a larger larger number than 8, right, because this one's 10, it's further away from 5, further away above the mean. Down here we've got negative values, meaning all of these values must be below the mean somehow. And then, of course, the further down, right, the bigger it is, or the smaller it is, actually, we should say, right, 0.769, negative 1.0, negative 0.256. So this one is actually the largest number, right, because it's negative 0.256, right? It's closer to 0 than these guys, because the number that we're looking at, 4, was closest to the mean. It's closer to the mean than 1, it's closer to the mean than 2. All right, so that's how you find the z-score, and it's kind of showing you, you know, how each of your numbers are positioned, how they relate to each other, you know, which one's smallest to largest, and also their position to the mean, right? Closer to 0 means closer to the mean. Further away from 0, further away from the mean, whether that's above or below. Okay, whoops. So we're going to pause. There's a problem for you to try on the next page. So we're going to pause before I slide up, and you're going to practice it, and ready to go. Okay. So if we look here, they gave us the mean and the standard deviation, which was nice of them, so we didn't have to find that on our own. So for Tyler, right, his z-score ended up being 1.625. Damien, his z-score ended up being 1.8. Now if we look, Damien's z-score is higher, right, further away from 0, above, you know, they're both positive. So we know that they're both above the average score in their class. But this one is more above than this one is. This one's further away from 0. So this one, Damien was higher in his class than Tyler was in his class. So even though Tyler's score was actually better, Damien, the question said who had a better position in their class. Damien had a better position in his class because his z-score was higher. He was above more people in his class than Tyler was. All right. This is another example of why having more information, more pieces of data, give you a better picture of what's going on. Okay. Because if we just looked at the z-score, you'd think Damien might have done better than Tyler, but then we look at the actual score and Tyler's score was better. However, you know, we do kind of see that since looking at the z-scores and looking at the averages for the class, right, this class has a lower average, and Damien's z-score was a little higher, so he did a little better in that class. It goes to show that maybe Tyler's not necessarily a better math student. Maybe the test for Damien's class was harder. Who knows? Maybe they had different teachers, and one did well and one did not. Who knows? So just another example. All right. Last thing we're going to talk about is this idea of normal distribution. All right, a normal curve, also called a bell curve because it's shaped like a bell, represents data that when you measure the data or you look at the spread of the data, it kind of ends up making this bell shape where the majority of your data falls right in the middle, right? This guy right here, this line in the middle kind of represents the mean, and then these numbers represent the standard deviation. So this is 1 standard deviation below the mean, 2 standard deviations below, 1 above, 2 above. So we see, you know, the closer, most of our data is within 2 standard deviations, and actually probably, and more than half is between 1 standard deviation, right? So some properties of this guy, right? It's a symmetrical bell-shaped curve, right, with a vertical line through the center that represents the mean, right? For a perfect normal distribution, the mean, median, and mode of a normal curve are all equal and right there at the center, right? In a perfect situation. In real life data, it might not be as pretty, but this is kind of the standard we use to measure by. So then we're going to look at this empirical rule, and we're going to use this. This is how we're going to use this information. If we look, it says about 68% of all data values of a normal curve lie within 1 standard deviation of the mean in both directions. So if we look here, 34% of the data is here, 34% of our data is here, 13.5, 13.5. So within 2 standard deviations, we have about 95% of our data, right? And then here, I had to change this, 2.35, 2.35, we have between 3 standards, or 3 standard deviations of the mean on both sides, we have about 99.7% of our data. That's where most of our data lies. Anything beyond that would be very extreme cases. If we were looking at data, those would be our real big outliers. Okay, so we're going to look at this. This is what this says. Most of our data falls in here. All right, so here's how we're going to use that knowledge. I think we're almost done. Last page, 2 more slides. So here's an example. Suppose that 300 chemistry students take a midterm and the distribution of their scores can be treated as normal. Find the number of scores falling into each of the following intervals. So within 1 standard deviation of the mean. So find the number of scores. So they could ask you a couple things. All right, within 1 standard deviation of the mean, right, we know this is where 68% of our data lies. So had they asked, oh, you know, if we picked a student at random, what's the probability they would be within 1 standard deviation of the mean? Well, 68%, right? That's where 68% of our data lies. Now here they asked us, you know, find the number of scores in that category. Well, 68% of the scores are in there. There's 300 scores. So 68% of 300 is 204. So 204 scores are within 1 standard deviation of the mean. Okay? And then second, within 2 standard deviations, same idea, right? If we're going with 2, that's where 95% of our scores are. And if you need to refer back to that other chart, you can. 95% of our scores are going to fall in there, right? So 95% of 300, 285 scores are in between there. Beyond that, there's our leftover, okay? So that's what we mean by, that's how we use the normal distribution, right? Kind of using those percentages. They could ask you a couple different things, right? What percentage, you know, what percentage of students are above, you know, if the mean is, of a test score is 75, you know, how many students, or what percentage of students got above 75? Well, 50%, because this is the halfway mark, right? If the standard deviation was, and I'm just making stuff up now, but if the standard deviation was 4, right? So that means 1 standard deviation up was 4 more points. And you say, oh, how many people are, you know, between a 75 and a 79? Well, 34%. So 34% of however many that was. Okay, so these are just different ways you could use this. Once again, if you look online, there's variations of the percentages. Some of them get real specific and do 34.1, 34.1%. For our purposes, we're going to stick with the simplified version. All right, so on the next slide, there is one for you to try. Pause, and we'll come back to it. Did you pause? We're back. Okay. And here's what we should have gotten there. All right. 75 was the average, standard deviation of 2. So every standard deviation you go, that's, you know, 2 more or 2 less, depending on how far away which direction you're going from the mean. So the probability that they randomly select a sample that's more than 75 grams, well, 50%. That 75 is the halfway point. More than 73, well, if we're at 73, right, remember there's 34% of our data right there. So this 50 plus that 34, 84%. And then between 71 and 79, okay, well, if about 95, we've said before, 95% of our data is within 2 standard deviations, and 71 and 79 would be at 2 standard deviations on either side, so about 95% of our data in between there. And even if you look back and you did 13.5 plus 34 plus this 34 plus this 13.5, you still would have gotten 95%.